As Nate said, my name is Valerie. I am in geosustainability at Google, and I am here to talk to y'all about the AlphaEarth Foundations model and our Satellite Embedding Dataset, which was just launched last week. And the goal here is we're trying to unlock the power of Earth observation data using analysis-ready deep learning. And we'll get a bit more into what I mean by that in this talk. And so, not sure how many folks here are already Earth Engine users, but if you do work in Earth Engine or in satellite analysis in general, you're probably well aware that we are not scarce on data. There was a time in the history of satellite remote sensing where people were working with just a few images at a time. You'd have to pay to buy them, and it would be very costly to get a large collection. But with the opening of the Landsat archive and the Copernicus program, Sentinel instruments having a free and open data policy, we now have more satellite imagery than we've ever had in the history of science and analysis in general. So on a single week, we get as many as over 100,000 Sentinel-2 images, and the collection now sits at over 31 million, 3 million Sentinel-1, 4 million Landsat 8 and 9, not even including the history. So just to give you a sense of scale, this is a lot of data. And the data volume does continue to increase. So as new satellites come online, more collections are added. Problem isn't going away. And the challenge we wanted to address in building AlphaEarth Foundations and launching the Satellite Embedding Dataset was being able to take all of this information, and rather than it sitting in individual images and everyone going through a ton of different steps to process it and make it ready to make maps and perform the sort of analysis we need to answer questions like how much forest are we losing in a year, or where is all of the surface water? We wanted to build a model that assimilates this data and makes it more usable. So instead of going to the raw observations, you'd have something more analysis ready. Enter AlphaEarth Foundations. So AlphaEarth Foundations, you can think of like a virtual satellite. And what it does is it takes all of these disparate data sources, these unique observations of an individual place, and it puts it all into a deep learning model that is able to include the measurement context, so optical, radar, LiDAR, spatial context, and temporal information, and make these information-rich embeddings that we host just like a normal satellite image, where it's got pixels and channels to it, though in our case they're axes, and you can use these for any sort of analysis you'd normally do with satellite imagery. And showing this in a bit of a different view, this is a figure out of our recently released paper. You can see these kind of disparate records, which are shown up on the top. We've got sparse data, it's non-uniformly sampled, different satellites are coming over at different points in time. We've got all of these different, again, radar, optical, we've got gravity fields in there, LiDAR observations. And what we want to be able to do is make this harmonious record where we've got a continuous monitoring period, and our model is able to compress all of that information and not just understand kind of the measurement and spatial context, but also summarize over a period, something that a real satellite actually can't do. You can't really take an annual picture, but you can generate an annual embedding with AlphaEarth Foundations. And so for those of you deep in the weeds of remote sensing, the next question is usually like, okay, tell me more about the sources. I've got the full source list up here on the left, including the different products and bands that we use. I already said this a couple of times, but it's a different mix of optical, radar, LiDAR, DEMs, climate information, gravity fields. We've got some land cover information for some weak supervision. And we also assimilate information from text sources. So we use geolocated records from Wikipedia and species observations and their associated species record from Wikipedia tied to the points from the GBIF, or Global Biodiversity Information Facility database. All of this is used in our learning process. Our pre-training data set for this model, as far as we know, is one of the largest ever created. It is over 3 billion individual image acquisitions. Those are spread across 5 million different sites with 2 time periods. So essentially 10 million individual video clips. So every image within a 1-year period for those training series. And of those, about 7.3 million have text and location information associated. Sentinel-2 is by far our dominant data source with about 1.4 billion observations, with big contributions from Sentinel-1 and Landsat as well. And I mentioned earlier, the model does include spatial and temporal context, unpacking a bit more of what we mean there. The model gets about 1.2 kilometers by 1.2 kilometers of spatial context as a field of view when it's generating an embedding for a given pixel. And so just to kind of see what that looks like in an image, if the red square is about a little bigger than a pixel, but at the center there, that's about how much information the model sees when it's creating that embedding vector. And when we're dealing with the satellite embedding data set, where we're summarizing a full year of imagery, that you can imagine you get many, many different views of the same place. And the model is able to use that series of images to encode a temporal trajectory. So things like phenology, seasonal snow cover, anything that the model is able to see through that series of images can be encoded as part of the embedding signal. And so, talking a lot about embeddings, we consider the image outputs of AlphaEarth Foundations, our virtual satellite embedding field images. So again, very different than normal satellite images, which have bands that correspond to physical measurements. These are images where each pixel is an embedding vector. So in our case, it's a 64-dimensional embedding space. So we've got kind of 64 bands in these images, each corresponding to one of the embedding axes. And we've got this continuous surface at 10-meter resolution of these embedding vectors. And going back to my first point about dealing with satellite imagery, this is a continuous field of embeddings. There's no cloud cover, there's no scanline gaps, there's no compositing necessary. It is just a continuous surface of these information-rich embedding vectors. And so I want to spend most of our time today talking more about the data set and what we can do with it. But in terms of the model, I encourage everyone to check out our preprint up on Archive. Talk to Nate, we're going to get the slides hosted for you later on the website. So all of the links and information will be available there. Thank you for throwing in the chat as well. And yeah, so you can think of AlphaEarth Foundations as this new foundation for analysis generating embedding layers that you can use in all of your remote sensing workflows. It's our virtual satellite. It can learn all sorts of patterns across different data streams, and those embedding images are kind of the core output. And those are what we have hosted in our satellite embedding data set. So the satellite embedding data set is a foundational data set for AI-powered analysis. So imagine we've taken our deep learning model, we have run it at scale, and so what you're getting is the output of that. You don't have to run inference yourself, you don't have to wrangle data sets. This data set is available in the Earth Engine catalog, just like any other image collection, and I got the collection ID down there. And of course, the next question becomes, what can you do with satellite embeddings? And so I said kind of standard remote sensing applications. Here we think of kind of our most common applications as similarity search. So this is a very common thing to do with embeddings in different domains, not just remote sensing and text, image search, that sort of thing. But the idea here is if you have a location, an embedding vector for a given location, you can compare that to other locations and instantly find places that have similar surface conditions, environmental conditions, temporal trajectories, spatial patterns, everything that goes into that embedding. We can now quickly compare embedding vectors to find things that are alike or very different. Can also do classification. So having an embedding data set means you can make very accurate maps with less training data, and I'm going to show you some examples of that. You can perform regression, so similar to classification, just instead of discrete categories, imagine you've got continuous variables like biomass or percent surface water, and you can use the embeddings to effectively interpolate those across a landscape and go from a small number of observations to maps at scale. And last but not least, our embedding data set is not just a single year. If I go back to the collection here, we actually have embedding layers going back to 2017. So there's a year, data layer for each year from 2017 to 2024. And by comparing embeddings between years, you can begin to easily identify deviations, not necessarily from place to place, like with similarity search, but for the same location at different points in time. And so we've put a lot of work into the model to make sure that the embeddings were comparable through time, and that unlocks a lot of these really interesting change detection applications. And before we jump into some more visual examples of all of those things, I wanted to call out that as part of our launch last week, we also launched a series of 5 tutorials in our Earth Engine community tutorials section, covering pretty much all of the topics I'm going to talk about today. So I'm going to give you kind of a whirlwind overview with some quick demos and code snippets, but you can check the website for the slides later to get back to those. And I'd encourage anyone who's interested to check out the tutorials and work through these on your own. They're really awesome, lots of great information and good code snippets and tips and tricks to get you started. So getting a bit more into the technical weeds before we get into the applications. Again, reminding you, we have 10-meter pixels. Each has that 64D coordinate. And another thing I haven't talked about yet is the fact that these embeddings are actually designed for clustering and tree-based classification. We incentivize the model to make sure that the vectors or coordinates in this embedding space are not just randomly placed, they're well distributed on what we call a unit sphere. So imagine it's a 64 dimensional sphere, and these embeddings are all unit length. So they have a magnitude of 1, which means if you're doing any sort of machine learning or other applications that would normally require some sort of normalization, you're not going to need that here. We're already unit length, we're already scaled, and that makes a lot of calculations and analysis with them a lot easier. Remember, the goal is to be analysis ready, in fact, easier than the raw satellite images themselves. And just a quick fun quote, I love this quote from Jeffrey, and on visualizing these spaces. You'll see a lot of spheres in my presentation when we're talking about the 64D space, and you can do what he does. And when you look at those spheres, just tell yourself 64 in your head and it should get you through. But really, I make the point about the sphere because, as I said earlier, when you're working with embeddings, they might look like satellite images, but they're quite different in the content of the image bands. And because we're dealing in vector space rather than the physical measurement space, we want to kind of shift our thinking from the classic, oh, if I wanted to difference 2 images, I would subtract. Instead, we're going to think about vector operations because we are actually working in vector space. Another thing just to flag as you're working with embeddings, they are linearly composable. So you might remember the example from Word embeddings with being able to add and subtract and do other operations on those. Our embeddings are similar when you aggregate up to different scales, and this is very relevant in Earth Engine, where pyramiding is a very important concept, that when you're aggregating up or down, you will preserve distance relationships between the embedding vectors. And so in the little example to the right there, you can see if we imagine taking a square that's aggregate that's composed of 3 or 4 pixels, 3 are forest, 1 is water, you would get something in embedding space that's probably closer to a forested wetland, because that kind of sits in between the kind of sub-pixel classes there. And you can also think of, like I said, virtual satellite or a learned PCA. So the first temptation when you see these 64-band features is, oh, well, run a dimensionality reduction. You can, but in reality, we've already done the dimensionality reduction. This was a huge volume of data that's been compressed into these 64 axes. So it's already as reduced as we could get it. Always welcome to explore there, but I think important to remember we've reduced the dimensionality quite a bit already, and those axes are designed to be uncorrelated and again, well distributed and semantically meaningful. So I think that's enough about the kind of structure of the data set. I want to share our first demo, which is my personal favorite, our similarity search demo. So again, this is where we're going to sample the embedding vector for an individual pixel and then compare that embedding vector to every other embedding vector in an embedding image, or if we're making a global mosaic of embedding images, it's literally every other pixel in the world. And so I'm thinking about that vector analysis space. How are we going to compare two vectors? We're going to use something called the dot product. Now, remember way back when math class at some point, you may remember comparing vectors. You want to be able to reduce the comparison down to a single number. And in this case, we are dealing with those vectors that have a length of 1. And so really all we have to do is multiply the two vectors by each other, sum the products of the individual element-wise multiplication, and you will magically get the cosine of the angles between the vectors. And in my little diagram here, you'll see when vectors are really closely aligned, you'll get a dot product closer to 1. There's 0 degrees in between the vectors. As you're about 90 degrees, so perpendicular, you'll get a cosine closer to 0. And then when your vectors are pointing in opposite directions, your dot product is going to be -1. And this just gives us a really quick and easy metric. It's very simple to calculate. Think of it as like the NDVI of embedding vectors, but really simple math here just to get us to a comparison of these feature vectors. And so in Earth Engine, just to show you what this would look like, it essentially is going to be sampling a point geometry. So code here is you're getting a point location. We've loaded the embedding collection. Worth noting, our main embedding collection hosts images, embedding images for the full time series of years. And so you do need to do a filter date in order to isolate the year of interest. And you'll see here, again, we're using a mosaic. I'll show you a little bit later. The collection's actually structured in tiles. And so in order to generate that kind of continuous global surface, we're going to use a quick mosaic here. And there's the meat of my function. Not sure if we can see my cursor, but the similarity is, as I said before, simple sample, multiply, sum over the products, and we're able to get an image now that is those dot products for the pixel of interest and every other pixel. Curious to know what this looks like. Here is my example. And again, you'll have access to all these code links later, but the example here is for Midtown Manhattan in New York, and we have a point that's kind of right in the Dentist Park. Think like Times Square area, towering skyscrapers, and you'll see that other pixels right around that area are lighting up. They have a dot product that's more closely aligned, so closer on the more similar end of the spectrum. And then you'll see the open water, some of the more green spaces, more suburban areas are getting into those darker, more purple tones, indicating a further deviation of the dot product. And they are in that case, less similar. And the script is really cool because it's super simple. You'll see it's just a few lines of code, but we also have packaged this. This is really fun to play with into an app just to make a bit more of an interactive experience. So taking that same point that I showed here for downtown New York, and looking at the similarity at a global scale, you'll see here for the Eastern US, we're lighting up almost all of the major cities, Boston, DC, kind of going down the coast. And it's not just things that are close by geographically. If I go across the country, in the US over to San Francisco, you can see downtown areas, more developed areas lighting up as similar to New York. Same goes for London, Buenos Aires, Tokyo. Really, we've essentially made a single click map of the densest urban areas in the world just by comparing their similarity in embedding space. And I would encourage everyone to play around, find some locations of interest to you, and just explore where else is like that in the world. This was one of my favorite apps coming out of the project. And I also see we've got a lot of questions coming in the chat. When I get through some content, then we can open it up for Q&A. But yeah, jumping back in. So for the similarity search, I didn't show this interactively here in the interest of time, but embeddings, as I said before, are designed to pyramids. So when you're zooming in and out in Earth Engine, in the similarity search, or any of your classifications, it's really great. Earth Engine's doing the aggregation for you. And at the same time, the embedding results are preserving their meaning. So as you're aggregating or zooming out in the similarity search, the results are essentially still valid at those coarser and coarser resolution. And kind of technical details aside, the important thing is satellite embeddings were designed to work well in the Earth Engine infrastructure. Again, back to that idea of making a really analysis-ready data set. Couple more examples, moving right along here. So imagine instead of just a single point and you want to find what's similar to that, imagine you have multiple points or you want to understand some of the underlying structure in embedding space. Unsupervised classification approaches, so clustering works really well, and embedding space was designed for that. And so here we can take a random sample using Earth Engine of just points in an area of interest and run a clustering algorithm with any number of clusters of your choosing. So here's a simple example using the Weka k-means clustering algorithm in EE. We've tried a couple different numbers of clusters, and the map that we're iterating through here shows as you add more clusters, more of that structure that's being revealed in this part of the landscape. So we've got lots of fields, a little bit of forest and water, 2 clusters, you kind of get veg, not veg. Few more clusters, we can start differentiating roads and other more linear features. And then at some point on the high end of the number of clusters, we're kind of finding all of these interesting patterns probably related to topography and moisture gradients. But again, nice way to explore the structure in the embedding space without necessarily needing to label it in a particular way. The little shout out to the tutorial on unsupervised clustering. You can actually use this to then go and assign labels, and there's a great example walked through there. You may be asking, okay, that's great. These are kind of interactive or fully unsupervised. What happens if you have your own labeled data? Well, you can use any of the supervised classification techniques. If you can do this with the Earth Engine built-in classifiers, things like random forest or support vector machines, we've got lots of built-in classifier options. I will say it is easiest to do this if you've got some sort of time information with your samples. As I mentioned, we've got these different years of embeddings in one collection. So I know you've got to be able to match your the time of your observations with the correct embedding years. But overall, this is a super low noise feature space, so you should be able to get really good performance with fewer labeled points than you would need for more conventional classification on composites or other remote sensing inputs. And again, please try those built-in classifiers before jumping to more custom models like neural nets you can host on Vertex, because our goal here was really to make it possible to not need a ton of parameters on top of the embeddings in order to get a good result. And just so that I've shown this, again, there's a lot of options in Earth Engine. There's great documentation on all of these and some guides as well on our dev site. So feel free to get in there and explore different options. And our tutorials, again, do a more detailed walkthrough of the steps. I'll just show kind of at a high level here, just to point out how simple this is. If you're, again, loading the collection in Earth Engine, get it down to a year of interest, bring in your feature collection with your labeled points. In this case, assume all of our points are in the same year. We run what's called sampled regions in Earth Engine, where we're actually extracting the embedding vectors for those labeled points. You can then, you've got a train test split, filter on that. Simply train a classifier. This is a random forest with 85 trees, and apply that classifier back to each tile in the embedding data set, and you will end up with a nice first cut at a classification map. Quick aside on the structure of the data set I mentioned earlier, we make a lot of mosaics out of it. It's actually hosted in these non-overlapping tiles. So if I show you just a little example here, these are all individual pieces of the big annual layer. And so if you're working in Earth Engine, you can map over a collection and apply things to each tile to improve efficiency. Or again, you can generate those big mosaics, but at the cost of it's a little less efficient to work with in real time. And going back to our classification example, here is the output for a tile. In this case, we used 150 points per class for about, I believe, 87 classes in the USDA National Agricultural Statistics Survey's cropland data layer. And we have, again, very small number of points, relatively speaking, only 150 per class for that huge number of classes. And I've got the result using the satellite embedding inputs on the left and the original data source on the right. There's definitely some differences there, but really for that low number of points, it's really impressive how good we are, and that you get a lot of coherence in the fields and details in the class structure. So again, encourage you to check this out, and got a little code example if you want to try this one and look around for yourself. And finally, again, last but not least, we've got those change detection examples. So mentioned earlier, we use the dot product for similarity search. Here we can use it for change detection as well. So it's our subtraction equivalent in vector space, and we're just looking at the divergence between the embedding vector for 1 year for a given pixel to a different year for that same location. And it's worth mentioning here that there's other ways to do these sort of comparisons in Earth Engine. We call them spectral distance functions. And we've got the spectral angle mapper, spectral information divergence, squared Euclidean distance, and Earth movers distance are all options in the sort of metric you can calculate. At their core, these are all kind of different variations on the same idea. In fact, I'll point out the spectral angle mapper is actually our cosine of the dot product, so very close to what I was showing before. If we apply these just for fun to see what they look like, you'll get a set of change maps that look something like this. So based on kind of the differences in how the metrics work, the results are somewhat different, but honestly, that dot product approach gives you really simple math and a really quick way to compare. So if you don't need to pull out any of the fancier alternate flavors, not necessarily necessary, but you can see here we're looking at some agricultural fields, and because those embeddings are encoding things about not just the surface properties, but temporal signatures, you'll see that looking across 2 years, you'll see changes in phenology light up as a change in the embedding space. So we got a lot of variability in fields. And with that, I moved pretty quick, so I think we'll have plenty of time for questions. Thank everybody for coming out tonight, and I can leave this up a bit while we talk. Again, we got lots of great resources coming out of our launch last week, so got some blog posts, our paper, of course, the data set in the Earth Engine catalog and the tutorials I have referenced. And if you are like, oh, I'm still getting caught up on what embeddings are and what they're for, I also linked to a nice blog post that I really like on just multimodal embeddings for text and image search, kind of separate from the satellite discussion. And with that, I'm going to get over into the chat.
There's a lot of questions in the chat. Do you want to just...
Yeah.
Do you want me to moderate them, or do you want to go back to the top and...
I'm good. Yeah, why don't we get back to the top here? All right, maybe we go through the questions in the chat and then we can take some hands. So let's start with investigating forest canopy height mapping using custom airborne 3D point LiDAR data and AlphaEarth embeddings. Yeah, so I'm assuming the question here is about, can we take forest canopy height information that you've gotten out of some sort of point clouds for a more localized area? This is the sort of thing that's great to try. And we've seen people succeed in this sort of use case already, where you can take kind of your small, very densely sampled, highly processed information, train either a regression model or a classification model, and then scale those measurements over larger areas. So if you've got those estimates of canopy height for your airborne survey, train a regression model, I would assume, on top of that, and then make a map either for a different year or a larger extent. Basically, the embeddings were built for that sort of application. All right, since the embedding vectors capture information at a location, are the bands positions within the vector interpretable? Oh, great question. So the order of the bands, the actual sequence, are not really interpretable. I often at this point when talking about this like to draw the kind of classic neural net diagram with all the nodes. Imagine those video sequences of images are coming in, they're being multiplied through all the weights in this connected network, much more complex structure than simple neural net diagram. But just going through all those transformations, and what comes out in the embedding vector is a learned combination. It's really not possible to pull apart the different pieces. And that's why we encourage people to think about them as a vector, not as bands or something that you're going to want to try and to tease apart, like different parts of the year or any specific meaning to the ordering. In fact, anytime you retrain one of these giant models, you could get a different ordering out of the space. So the order doesn't matter, but the collective package does, and that ordering is preserved, I should say, from year to year, which is why we can do change detection. So axis 1 means the same thing in different years, but like you can't necessarily compare it to some totally different embedding space and have meaning. Yeah, and seconding that question, what the embedding dimensions represent, they're an aggregate of all the things. I do think there's still opportunity to research correlations with particular features or temporal signatures, but keeping in mind those are a combined learned signal that's compressing across all the things it was learned from. Question about clouds in embedding space. So one of the advantages in our learning setup and the fact that we have a super small embedding space, relatively speaking, there are no clouds in embeddings. That information does not make it through. It does not get passed into the embeddings. And so our model is able to learn how to reconstruct images with no clouds. And so there's no noise the way you would be used to from a normal satellite image here. It's just a smooth representation of the surface properties, and we've already kind of removed all of the noise and other interrupts in the signal to give you that really clean feature space. All right. Are the embeddings ordered in decrease order of explained variants like PCA, or do they explain all the variants in the original data? So they're not ordered, as I mentioned before, in a particular order of variance. And they are, so there's always going to be more noise in the original source data sets. In fact, that's part of the goal of having the embeddings in the first place, is to learn away things like the atmospheric effects, the cloud cover, the artifacts, the speckle in radar imagery, and get at this more truth signal of the surface conditions. And so they don't explain all the variance because they really shouldn't. In fact, we're trying to reduce the signal down to just the most meaningful properties. And so I think maybe the better thing to think about is how much of the variance in your processes of interest are explained by the embedding. So if you have those forest canopy measurements from the first question, and you're doing some sort of regression, how much variance in the predictions of biomass or canopy height are explained by the embeddings are the more interesting question to ask. For the Similarity demo, does it work on infrastructure in marine areas, or is it specialized for land use? That is a great question. So I didn't mention this very specifically earlier, but the Satellite Embedding Dataset covers Earth's terrestrial land surface and shallow nearshore waters. So we did our best to include coastal zones, small islands, coral reefs, intertidal, so places where you're getting switches between land and water. So if there's infrastructure in marine areas that would be associated with, again, like small islands, or we use the intertidal data set, the Allen Coral Atlas, and some bathymetry information kind of define what was our global coverage extent. Like if it's in those areas, then yes, but kind of those open water portions of the world are not covered in the Satellite Embedding Dataset as it's released now. Is the data available in Earth Engine only? Can you access as a cog or somewhere else? Currently, it is a collection in Earth Engine designed to be incredibly interoperable with the Earth Engine ecosystem, but we are hearing these requests for making it available elsewhere, and we definitely want the data to be as useful as possible. So yeah, stay tuned, and we're looking into options there. Exciting work. NASA just dropped Galileo, which uses embedding models from multimodal data, but separates global and local features. How does this compare to AlphaEarth's unified architectural approach? And are there plans to make the encoder model directly available? I think I've got one of my colleagues from Google DeepMind on the line, and I want to see if I can throw this question over to get a better answer on the modeling structure there. Chris is one of the authors, or the lead author on the paper. You on the line, Chris?
Yeah, can you guys hear me? Am I coming through?
Yeah.
Cool.
I'm taking this one.
In the shadows. Sure. So just to be clear, the AlphaEarth Foundations work is an embedding model. So I think there's a lot of great work around GeoFoundation models. There's a very excited, motivated community working on that. And I know Galileo, actually that's from February, maybe from a little while ago, is kind of building this sort of pre-trained backbone checkpoint design for applying to Earth, GIS problems is the right way to say it. So I think it's a very kind of different thing, and I wouldn't compare them too much. So for example, AlphaEarth Foundations is designed to, you almost task it like a virtual satellite. That's the idea. And so for an example, if you're missing some data, if the sensor is completely gone, it doesn't really matter. Even as you move across the Earth with the sort of varying conditions, you get this sort of continuous embedding field. And that's sort of the goal of the model, is to be this artificial satellite. I think Galileo is a great example. Plenty of other GeoFoundation models aren't really designed to be used like that. They're designed to be this more backbone that you then maybe stick an MLP on or something else, and then fine tune that. So I wouldn't compare them too similarly. I think, yeah, I know the word foundations is in the name, so it doesn't help a whole lot. But I would consider it more as really this sort of embedding field model. That's the idea, is that we're generating these virtual satellite layers rather than giving you this pre-trained checkpoint that you can fine tune something on it. And really, to get a useful output, you do need to fine tune something on top of it. So that's maybe the way I would put it. So, in terms of, is the objective that maybe one approach uses versus our approach uses, how would we compare them? If it's an embedding approach, then it's a little easier to comment on. It's hard to say. We didn't do a whole lot of, maybe attaching kind of like the Pangea paper. You're sort of supposed to put this decoder on it and fine tune the decoder. We didn't really do any of that. So it's kind of hard to say how the choices we made would affect the more traditional foundation model fine tuning approach. But I think for the types of clustering, linear correlation type workflows, the AlphaEarth embedding fields work pretty well. So I know that's sort of an indirect way to answer the question. And I guess the last one was, are there plans to make AlphaEarth's encoder model directly available? Not currently. I think that dovetails into some of the other later questions, though, about more granular data, kind of going into that tasking thing, which I think Val can say more about. Hopefully that answers your question.
All right, thanks, Chris. Yeah, I guess building off of that, if this is an annual data set, is it suitable for direct use in studies of short duration extreme events like earthquakes or floods? The answer is yes and no. So within a year, we are capturing those temporal signals. So you can imagine if you've had a flooding event or an earthquake that's got, after effects, that we are going to see those in our series of imagery. And so, yes, you would get some signal from those events, and you might be able to tease that apart, find other places that had similar timing. But really, if we're talking about kind of monitoring, as Chris said, we are looking into ways that the model and data sets could be more useful. And so this is an active area. We're listening a lot to what people would want to do here, and that idea of, would you want to task more frequent updates? Would it be monthly, weekly, quarterly, that sort of thing, or kind of before or after these more extreme events? And so stay tuned. Like I said, we're looking for signal there on what people would want to use those shorter term aggregations for, in addition to the value you get out of having that like larger annual aggregation. Okay, another great question on near real time. So I understand from the paper that the model should be usable for near real time, but that capability is not exposed. Yeah, as we just saw, we're very excited about all of the possibilities here, and we really want to understand what the use cases would be. So we're starting with this annual embedding data set, but the model is capable of producing those finer granularity aggregations. And the more we hear, as with many things on Earth Engine, from our user community, what are the amazing things you want to do with this? What are the real world applications, the sorts of impact you might be able to have if you had a finer resolution? Yeah, please feel free to request things. There's data set requests on the forum, that sort of thing. Building off of that question, is there a plan to release each new year going forward, or even more frequently? I think gotten the frequently bit, but yes, we are planning to generate a new year of data early next year. So the hope is we'll continue to produce these annual layers and add to that annual data set. And so yeah, early 2026, we should see the 2025 layer being added to the collection. Can we create embeddings on our own small data sets? Yes, so again, going back to we're looking into options there. And you'll state if there's announcements, definitely you'll hear them on various Earth Engine forums, that sort of thing. With so many diverse landscapes in the world, how is it possible to make the embedding space consistent? I would attribute that, and Chris, feel free to jump in if you want to add more here, but I would say our sample is large. Like I said before, it is the largest that we're aware of, with more than 3 billion observations, global distribution of sites. And so we really did try and target the variability globally. From the paper, you can read more. We actually stratified our sampling of the locations to cover ecoregions. So it's a stratified sample based on the ecoregions, a couple of other supplemental data layers to make sure that we were getting representation of those intertidal zones, corals, other distinct ecosystems. And that really contributed to being able to create a space that does represent all of those different properties.
Hey, Val, I don't know if you wanted me to also try.
Yeah, do you want to add anything
You said
there?
my name, so I didn't know. Yeah, so one thing we didn't test rigorously, I think the sort of the spirit of the question is what sort of happens if I label some things in one continent and then I look at another continent and can tell you what happened. So we have our evaluation, it's in the paper, it'll tell you a little bit more, covers a large geographic area, much like the training sample. So we have a bunch of data sets. There's like an emissivity data set, there's a global land cover data set, there's oil, like all these different data sets that cover large geographic areas. So within those data sets for those problems, given the areas they cover, we can prove out that, hey, you get a good result when you have a data set that has this geographic variability, which to us was a good signal for this is useful for map making. The thing we didn't necessarily test, and would be great if someone else did, we can give you anecdotes on what we found, is what happens if I just train in this little tiny region and then I zip 180 degrees to the other side of the world, and how good is the performance over there? Anecdotally, I think, Val, you also, if you have an opinion here, it seems to work pretty well if you're in the same latitude. The results tend to be quite consistent. But again, the sort of tests we did were trying to follow a typical mapping workflow where you have some reference sample and then you want to apply that to the same region in which the reference sample was collected, or at least you don't want to extrapolate too far out of, to Val's point, an ecoregion that you from within which you've sampled. So hopefully that explains a little bit more.
Yeah, I'm also going to throw the next question to you. Is the model suitable for forecasting?
So another thing we talk a little bit about in the paper, it's kind of buried in there. So suitable for forecasting, that's another thing we didn't rigorously evaluate. So I don't want to make any claims about whether it can or cannot forecast. Also, a lot of forecasting, depending on what you care about, is strongly driven by climate trends. And given the sort of context of our model, I wouldn't expect it to do super well with guessing sort of the direction of weather at a really large scale. However, during training, one of the objectives that seems to improve embedding performance, but did for us, was to include a forecasting objective. So we want to take 6 months of data and predict what the embedding should be in the next 6 months. And this was based on the student-teacher training setup that you would probably read about in the paper. So the teacher would see what happened 6 months into the future, the student did not. And if the student tries to predict that forecasted embedding, do we get a better result? And at least the representation space seems to be better designed when we do that. However, is the forecast any good? We did not actually test that.
Yeah, moving along. So why 64 dimensions? How did you decide on that number? We actually get this one a lot. We did try larger embedding dimensions. Spoiler alert, you can eke out some better performance if you have a larger embedding vector, but really 64 was our sweet spot between getting really strong performance and being able to actually use these embeddings in the sort of workflows that remote sensing practitioners are already using. So when you get that dimensionality too big, first of all, you start encoding other things, you're not getting as clean a signal necessarily, and it's hard to train a random forest or a clustering algorithm on those even higher dimensional spaces. So we struck a balance between good performance and performance for kind of that built-in Earth engine, classification, change detection, regression workflows that we are hoping to help supercharge with these AI capabilities and the embedding data set approach. And so 64 is just a good sweet spot, and it works well for built-in Earth engine algorithms. Asking about if the embeddings are aggregated over the year, how can we analyze seasonality, summer months, winter months? The most kind of straightforward answer is bringing your label data to match the cadence of embedding. So what do I mean by that? In a kind of classic example of this we've heard is crop classification. So if you're getting kind of sequences of crops in different periods, rather than saying, okay, this is corn and this is soy in these different months, you might have something like double cropped corn and soy over the entire year. Similarly, for like seasonality, the similarity search is a way that you could say, hey, I'm aware of, you know, an interesting seasonal pattern for this location. You can use that dot product similarity to find other locations that have a similar seasonal pattern, similar temporal trajectory, plus similar surface conditions. All of that said, this also goes back to what I was saying earlier about the model is capable of generating those shorter cadence summaries. And if there are use cases that you really do need finer resolution, make those requests for an updated cadence data set. And we're definitely looking for applications that would be enabled there. How can overfitting be avoided? Does the vector approach reduce overfitting in small data sets? So overall, I mean, it's going to depend on the number of data points you have. You now have a 64D feature vector. It is, again, a very clean signal, but it's similar to any classification or learned analysis. It's going to always be a function of the dimensionality you have and the number of points that you are using for your classification. Chris, is there anything you want to add there on classification overfitting?
The cop-out answer, yeah, I kind of feel the same way you did. It's sort of up to you what you're doing. Again, the representation, we've published our metrics and exactly what we did to evaluate the data set. You know, you could take, here's a great example. You could take a problem that AlphaEarth Foundations, the data from AlphaEarth Foundations really accelerates your application on because you didn't have to, whatever, composite a bunch of data. Then you draw a small sample. It seems to do really well. Great, you know, this is awesome. Suddenly you draw too many points in the area you care about and you look at a different area and it didn't do a good job. And so I would say when you are concerned about overfitting using the data set, other than hopefully reducing the data volume needed to get a good result, which in turn, sort of Val suggested, can have the impact of reducing overfitting, it's still kind of on you to make that decision if you're going to use it to run a proper classification. And I think that's, yeah, I think that's all I'd want to say there.
Yeah. Thank you. Question about plans to release the code and the model. No current plans, but we are always looking for the best ways to surface our technologies. And so, yeah, right now we're focused mostly on making the data set available. We think that's really the most valuable thing to come out of the model. But that's next question. Process for using the model to extract embeddings from non-satellite data, minerals, vegetation, sample spectra that's been composited to Sentinel-2 Landsat. Sure, I totally follow, but I think in the spirit of if you want to interpolate measurements or other data sets, we've done some examples of that. Our evaluations include things like proxying the OpenET ensemble, as well as the ASTER global emissivity data set. So if you want to make those data sets for different years, or yeah, like be able to scale up without having to run all of those ensemble models, can do things like that. The other thing you can think about here is if you have other non-satellite data sets and you want to have them as inputs to a classification, the embeddings are a feature vector. So just like any feature vector, you can tack other things onto it. So if you have a supplemental data set that you think is going to improve your classification, doesn't necessarily have to be encoded into the model. You can use it as a kind of supplemental feature in the feature vector. We consider a Landsat dominant model, so we can explore back to 1990. Would love to see more historical coverage. It's currently not in the plans, but again, register those interests. Tell us what capabilities, what things you'd be able to do if you had that data set. And we're always listening to how we can continue to make this work more useful for everyone and have great use cases. I already answered a bit about bands. I know we're running a little low on time here. Answered about code. Quick one. How should we refer to the model? The model is the AlphaEarth Foundations model. So AlphaEarth Foundations is the name of the model. Satellite Embeddings is the name of the data set. So, but again, the AlphaEarth Foundations produces the satellite embedding data set. It's a great question, though. Thanks for asking. Talked about resolution. Bias in the training data and how that might affect embeddings, that species occurrence points are biased towards cities and accessible areas. We did strike a balance between, we had places where we had text data that's related to the species observations and where we had Wikipedia. Definitely know about the biases towards those urban areas, more populated places. So we didn't oversample locations where we had text information. We focused on kind of picking up as many text observations as we could. And then we also supplemented our sample with observations or locations randomly sampled from areas that weren't covered by the Wikipedia or GBIF data. And so we did balance that. And the locations of our training sample, not the entire data set, but just like where the samples were drawn, are available as supplemental materials in the paper. And there's a link there. So if you just want to see where they were, there's some maps in the paper as well. But yeah, we definitely tried to make sure that we were representing not just those populated areas, but the rest of the ecosystems as well. Running really quick, I know we're super low on time, but impact of surface reflectance versus top of atmosphere and resulting embeddings. We do use all top of atmosphere data. In deep learning, we can learn away the noise of the atmosphere. And so, yeah, we never really, we try to avoid adding additional models into the process when we've already been throwing a big model at this. And so all of our data is on top of atmosphere. And we really don't think it's necessary to then apply an additional process to get that to surface reflectance when we're learning so much in the actual modeling process that we're doing here. And last one, how does it go comparing northern and southern hemispheres? We do preserve temporal trajectories, so the phonology is going to be shifted northern versus southern hemisphere. I wish I had a few more minutes to go into the similarity search and show you, but I encourage you to click around some vegetation. You'll notice like there's a much stronger vegetation signal. If you click a forest in the northern hemisphere, you'll get more northern hemisphere forests. If you do the southern, you'll get more southern, just because of that offset in phonology. But usually you can overcome this by adding more representation. So if you want a global forest map, make sure you're clicking northern and southern hemisphere, and that usually reconciles the result. But realize we're at time. Thank you all for coming out for the talk, to Nate and Scott for hosting and sharing all the links in the chat while we were going. Some really, really great questions here.
Thanks so much, Valerie, and thanks, Chris, as well, for jumping in. And I look forward to seeing what everyone does with this moving forward. All right. See you, everyone. Thank you.